This is the 8th section of the integration chapter, which is about finding areas. So you'll remember from year 1 that if you have a function or a graph, so let's say we've got, x, why did I put y there? And let's say we've got some sort of graph function that looks like this, and we want to find the area between two limits, which we'll call a and b. So you want to find this area here. What we said was that we can find it by integration. If this is the graph of f of x, then this area is given by the integral of f of x between the limits of a and b. So we can find the area. I think also in year 1 you also looked at finding the area between, I think, a line and a curve. We're now going to be looking at the area between two curves. So let's say I had a curve like that, and let's say I had another one that went like this, and I want to find the area between them. Okay, so let's say I want to find out this area here, like that, and let's say that this is the graph of g of x and this is the graph of h of x. There are two ways in which we can find that area. Let's spell area right for a start. Area. We can find the area underneath the top curve, g of x in this case, and subtract the area underneath the bottom curve or graph. Do this. Or what we can do is we can actually subtract the functions first, then integrate. So what I mean by that is you take the top graph, subtract the bottom one, work out what that is algebraically, and then integrate. My preferred method is this one, because it means you only need to integrate once. So whatever this function is, you subtract the one at the bottom and then you integrate it. So basically it's the integral of the top minus the bottom worked out algebraically, and then dx. Now also in this section they've snuck in a bit to do with integrating parametrics. It really deserves its own section, really. So let's go through that. Integrating parametrics. Now you know how to differentiate parametrics, so don't know if you remember, we said that if we differentiate parametrics it was dy dx equals dy dt divided by dx dt. I don't know if you remember that. Okay, that's differentiating parametrics. We also want to integrate parametrics. Now remember, we can use like the dy dx, dy dt. We can actually think of that as fractions so that we can sort of multiply them out and simplify and things like that. So we actually want to do this, y dy dx. Oh, sorry. We want to differentiate what our function of y is with respect to x. Now if it's a parametric, we can say, right, okay, that's the same as y dx dt with respect to t. Now if you were to multiply this out, it becomes the same as that, but what we have here are things in terms of parametrics. So y is going to be a function of t, and this bit here is going to be, well, if x is a function of t, then dx dt is going to be that function of t differentiated. So what you'll have with a parametric is actually an expression in terms of t, which you can then integrate. So y part of the parametric doesn't change, that just goes straight in. The x part of the parametric you differentiate. you multiply the two together, so you'll have something in terms of t, you integrate it. Okay, now because this says dt here, if we have limits, those also should be in terms of t. Okay, so since we are differentiating with respect to t, our limits must be must be t limits, so there must be values of t, so watch out for that. So I'll just put must be t limits. Yeah, so that covers everything in this section. Finding areas, whether it's underneath a single curve or between two curves, integrating parametrics, and it could now cover finding area. It could be any of the methods that we've done so far. So reverse chain rule using patterns, partial fractions, integration by parts, trig identities. It could be any of those. First thing we want to do is to write down what the actual integration is. We have limits of 0 and 4. This is the equation of the curve. So this is what we want to do. R is equal to the integration between 0 and 4 of 9 over the square root of 4 plus 3x dx. Now I recognize this one. If I bring the bottom here, write it to the power half, and bring it to the top, bring the bottom to the top, it will become 9 times by this to the power negative a half, which I can use the reverse chain rule for, because this bit in the bracket is linear. If it wasn't linear, if it had like 3x squared or something like that, I would have to use a different method. Okay, now so that becomes 0, 4, and then 9 times by 4 plus 3x to the power negative a half dx. Now you could sit and try and memorize all sorts of rules about if you see this pattern do this, if you see that pattern do the other, and just remember rules. It is better just to practice. The more you practice, the more you will just recognize and know almost instantly what to do. So just practice lots of integration questions. Don't try and sit and remember rules. Yeah, so let's integrate that using the reverse chain rule. So we integrate the outside. So if you integrate the outside, that means the power becomes a half. You add 1 to the power, and then you're going to have 9 divided by a half. We'll tidy this all up in a moment. That's integrating the outside. Remember, the inside of the bracket doesn't change. And then we divide by the inside differentiated. Now the inside differentiated is 3, so we're going to divide that by 3. This deserves tidying up in the bracket before we go any further. So 9 divided by a half, which is like 9 times 2 is 18. 18 divided by 3 is 6. So I will have 6, and then 4 plus 3x to the power half, and we've got that between the limits of 0 and 4. So now we're ready just to substitute those values in. So we'll have 6, and then 4 plus 3 times 4 to the power half, minus 6 times by 4 times 3 times, sorry, not times, 4 plus 3 times 0 to the power a half. So let's work that out and see what we get. So 6 bracket 4 plus 3 times 4, and that to the power of a half. So 1, 2, and we're going to subtract from that 6 bracket 4 plus 3 times 0 which I know is 0 anyway. Should have just been 4 in the bracket, to the power a half again, 1/2, and that gives me an exact value of 12. That's nice. It seems always happy when you get whole number answers. It seems correct, doesn't always mean it is correct, but it sort of gives you confidence. So 12, and since it's an area, we don't know what the units are, so we just put 12 square units for our answer, whatever those units are, centimeters, meters, miles, light years, whatever. So there we go. No, you can't have an area of light years. What am I talking about? This is the area between two curves. The curve at the top is sine 2x, sine 2x. The curve at the bottom is this sine x, cos squared x. And the limits are 0 and pi/2. I can see them here and here. So we want to integrate between 0 and pi/2. Now I'm going to subtract the functions, then integrate rather than the other way around. So the top curve minus the bottom curve, sine x cos squared x dx. Now the sine 2x I can integrate quite easily, that's not a problem. I'm thinking about how to do this. Now it does fit this pattern. Do you remember? They call it reverse chain rule using patterns. So it fits this pattern with some sort of k, value of k at the front. So I'm going to try what's in the brackets to 1 higher power n plus 1. So I'm going to try cos cubed to do the second bit. I suppose we could use substitution. You make u equal to cos x, but using the patterns is quicker. Right, so the sine 2x integrated, well, if you think of the sine being the outside, so you integrate this outside, that gives you negative cos. The inside of the bracket doesn't change. Then you divide by the inside differentiated, so you're going to divide by 2, so you're going to have a half, and that negative from integrating sine, so that's that bit done. For the second bit, I'm going to try cos cubed. So I'm actually going to put plus cos cubed for a minute, that sign might change. Try cos cubed x. Now I'm going to write my working in blue up here. So if I try cos cubed x, if I differentiate that to see how good my check is, so if I differentiate that using the cos rule, the chain rule, which means I write it like this, cos x cubed, so I differentiate the outside, so I get 3 cos x, inside the bracket doesn't change, squared, times by the inside differentiated, which is minus sine. So that's what it gives me. So it gives me this. Okay, I need to compare it with what I actually want up here. So that's what I actually want. So what adjustment do I need to make? I need to divide it by 3. I get the right sign, I just get a 3 there that I don't want. So the sign is correct, so I don't need to change the sign, but I do need to put a third here. Right, so now that's been integrated, and now we're ready to substitute in our limits, 0 and pi/2. So we'll get negative a half cos 2 times pi/2 plus a third of cos cubed pi/2. So that's going to be from the putting in the pi over 2 minus, now we'll put in a 0, minus a half cos 2 times 0 plus a third cos cubed 0. It's not theta 0. So I'm going to put that all in on the calculator and see what I get. And that gave me 2/3. Now that took me ages to work out on the calculator. I reckon it would have been so much quicker just to work it out manually, and I'll do that down here to show you how you do it. So you got negative a half. Now 2 times pi over 2 is pi. Cos of pi is let's think about -1. I've been fairly quick to do that, and then we end up with cos of pi over 2, which is 0. So you basically get a third times 0 or 0 cubed, and so on. Yeah, that would have been quicker to probably work it out manually that way, but yeah, as it goes, final answer is 2/3, and like before, we're going to say it's 2/3 square units, whatever those units are. So here we're going to use this formula here, because we've got a parametric equation. So we need y, which we've already got, and dx dt, which we need to work out. And what we need to watch out for is the limits. These limits are x limits, because our formula here says dt, these limits need to be t limits. So I suppose what you could say is, right, if you've got x1 and x2 here, these are your limits in terms of x, this is what you want to find, then actually these limits need to be t1 and t2. So you're going to have to use the x part of the parametric equation to change those values of x into values of t. So the first thing we're going to do is write down what y is, because that's not going to change. So y is just 1 over 1 plus t, that's fine. Now x is t1 plus t. I need to find dx dt. Now I suppose I could use a product rule, but it's much easier to just expand the brackets, t plus t squared. So that means that dx dt is going to be 1 plus 2t. Then the other thing I need to do is to change the limits. Now when my x value is 0, I need to work out what that t value is. So what do? I plug it into the parametric equation. So I've got 0 equals t 1 plus t. Now for that to be the case, I've t is 0 or t is -1, but the question says up here that t is greater than or equal to 0, so we don't have that one. So when x is 0, our t limit is going to be 0, and when x is 2, that means 2 equals t 1 plus t. So I reckon we can move the 2 across, make it a quadratic. So that would give us t plus, or t squared plus t minus 2 equals 0. Now I think we can factorize that, t and t, and I think we're going to have 2 plus 2 minus 1 equals 0. So we're either going to get t is -2 or t is 1. Again, because t is greater than 0, we ignore that. So we now have our t limits. We just need to make sure we put them the right way round. Now since x was the lower x value, it needs to be, t needs to be the lower one, and since 2 was the limit that would go at the top, this needs to be the limit that goes at the top. Now what you need to watch out for, let's say for example this was the lower t limit. If this number happened to be bigger than this one would still go at the bottom. So don't think, alright, with limits the biggest number always goes at the top, the smallest one goes at the bottom. That may not be the case, because a lower x value here may actually give you a bigger t value. Keep their positions the same, don't move them around and think, alright, I've got to have the biggest number at the top. That is not always the case. So now the question becomes integrating between 0 and 1 my t limits, y, which is 1 over 1 plus t, times by dx dt, which is 1 plus 2t dt. So we are going to write it like this, 0, 1. So we'll have 1 plus 2t over 1 plus t. Now this happens to be an improper fraction, which we need to deal with first, and to integrate it we're probably going to have to use partial fractions. Well, no, we don't need to, because we've only got one factor at the bottom, but definitely we need to deal with that improper fraction. So let's do the long division over here, get the quotient part out. So we're doing 1 plus 2t. Let's write it the other way around. Let's get the powers all the way around. So we'll write it as 2t plus 1 divided by t plus 1. That's better. So t's into 2t go twice, and then we'll multiply that by 2. So you've got 2t plus 2. We'll subtract. So we'll end up with 1 minus 2, which is negative 1. So what we have now is 1 plus 2t over 1 plus t is the same as the quotient, which is 2, plus the remainder over the divisor. Now the remainder is negative 1, so we're going to put minus 1 over the divisor, which is 1 plus t. So we actually don't need partial fractions because there's only one factor at the bottom. And then we integrate that. So, got to try and stop saying so. The 2 becomes 2t. For the next bit, we're going to try log of the bottom because it's like f dash of x over f of x. So if I tried log of 1 plus t, that would give me 1 over 1 plus t, but I need to make sure I get a negative, so I'll put a minus sign there. So there we go, no adjustment necessary between 0 and 1, and from there we can substitute the numbers in. So we'll have 2 times 1 minus log of 1 plus 1, which is 2, minus 2 times 0 minus the log of 1 plus 0, so that's the log of 1. And does it say, oh, it says the exact area. Right, so the second bracket, well, that's just 0, so that disappears. Log of 1 is 0. I suppose I should have some closed brackets there like that. So the whole of the second bracket is 0. So you basically just end up with 2 log 2. There's our exact answer. 2 minus log 2. Don't need the modulus sign anymore because 2 is positive. So there we go. 2 log 2 is that exact area. Right, so exercise 11H you can now do on pages 315 to 317. So I suppose let's just write down here the integrating parametrics, that might be useful. So y dx, and we'll put x1, x2 here, and that needs to be written in a form t1, t2, y dx dt, dt, and I think that's it. We had some other stuff about the areas between curves, so maybe if we just summarize that here. So let's have our function there, which we'll call f of x, and we'll have one down here which we'll call g of x, and if we want to find the area between the two, like this, where this is a and this is b, that area is equal to f of x minus g of x. Work that out algebraically, and then we'll integrate between a and b.